Alright, welcome to the next video in our classical mechanics series, and in this video we're going to talk about Newton's laws and then work a few examples using Newton's laws of motion. So Newton's first law of motion says that a force on a particle is equal to the derivative of that particle's momentum with respect to time, where the momentum is equal to the particle's mass times its velocity. Of course, if mass is constant, then the force is equal to mass times the derivative of velocity with respect to time, because the mass comes out of the derivative, which is equal to ma. And so we get the familiar F equals ma equation that you remember from intro physics. Newton's second law of motion tells us that if the force on the particle is equal to 0, well, then the derivative of its momentum with respect to time is also equal to 0, which tells us that the momentum must be constant. This is called the conservation of linear momentum. And what this means is that the particle is going to move in a straight line trajectory at constant velocity. In other words, a particle in motion will stay in motion and a particle at rest will stay at rest until some force comes and acts upon it. Newton's third law of motion says that if we have two objects that are exerting a force on each other, A and B, then the force that object A exerts onto B is equal in magnitude but opposite in direction to the force that object B exerts onto A. Alright, so those are Newton's three laws of motion. It's that simple, and now we're just going to work a few examples. The first example is free fall without air resistance. To set the problem up, we're going to start with a particle of mass m at the origin of our coordinate system. Here's our y-axis and here's our x-axis. And we're going to launch our mass m at an initial velocity v0 that makes an angle theta with the horizontal. The first thing we should do is identify our forces. Well, the only force that's acting on this particle is gravity, and because gravity points down and down is the minus y hat direction, our force of gravity is minus mg in the y hat direction. Now the next thing that we need to do is to identify our initial conditions. Now we know that the particle starts off at the origin, so x0 equals y0 equals 0. Now we need to determine what our initial velocities are. We can use our special angles to determine what these are. Now if theta were 0 degrees, then v0 is going to lie entirely along the x direction. So v0 would be v0 in the x direction. And if theta were 90 degrees, then v0 would be entirely along the y direction. So v0 is v0 in the y direction. So this tells us that v0 in the x direction is equal to v0 cosine of theta. And v0 in the y direction is v0 sine of theta. Make sure you're comfortable with that. So the next thing we need to do is to write down our Newton's laws. So along the x-axis, what do we have? Well, we have no forces. So mass times the acceleration in the x direction, which we learned from 2 videos ago, is just x double dot is going to be equal to 0. In the y direction, my double dot is going to be equal to minus mg, because that's the only force in the y direction, and it points down, so minus mg. So now we can solve both of these equations and plug in our initial conditions to determine x as a function of time and y as a function of time. So solving the first equation, we can divide both sides by m, and then we have x double dot is equal to 0. But we can integrate both sides, and we get x dot is going to be equal to a constant of integration c. Plugging in our initial conditions, we get x dot at 0, remember this is the initial velocity, it's going to be v0 cosine of theta, which is equal to c. So there we have that x as a function of time is just v0 cosine of theta. Now we can integrate again, and we get x as a function of time is v0 cosine of theta times time, plus another constant of integration we'll call c2. But of course the initial position is just 0, it starts off at the origin. This is equal to c2. Position, x of t, is now v0 cosine of theta times time. So there we have x as a function of time. Now we can solve the second differential equation. Dividing both sides by m leaves us with y double dot is minus g. We can integrate both sides and we get y dot is equal to minus gt plus the constant of integration we'll call beta. Y dot at 0 is equal to its initial y velocity, which is beta, which is equal to v0 sine of theta. So we get that y dot as a function of time is v0 sine of theta minus gt. We can integrate again and get y as a function of time. It's going to be v0 sine of theta times time minus 1/2 gt squared plus second constant of integration we'll call beta 1. Of course, the initial position is 0, so y of t is just v0 sine of theta times time minus 1/2 gt squared. So now we have x as a function of time and y as a function of time. Another good question to ask is, how far will this particle go? What is its trajectory? Well, to find that, we need to first determine what y as a function of x is, and then set that equal to 0 and solve for x. So what is y as a function of x? Well, to determine that, we need to actually solve the x equation for t, and then plug t into the y equation. To solve the first equation for t, we can divide both sides by v0 cosine of theta, and now we can plug that into y as a function of time. Doing that yields y as a function of x is going to be v0 sine of theta times x over v0 cosine of theta minus 1/2 times g x divided by v0 cosine of theta squared. The v0's cancel, sine over cosine is tangent, so y of x just becomes x tangent of theta minus 1/2 g times x divided by v0 cosine of theta squared. All right, we can set this equal to 0 and solve for x that makes this true. We can do do some rearranging, and we find that x is equal to 2 v naught squared tangent to theta cosine squared theta divided by g. All I've done was add the 1/2 g x over v naught cosine of theta squared to the left-hand side. I divided both sides by x and rearranged for the x that was left over. Using our trig identities, this becomes v naught squared sine of 2 theta divided by g. So this is an expression for x, so how far it's going to go along the x direction if we know its initial velocity and we know what angle it's launched with. So suppose now we want to know at which angle should we launch this mass with in order for it to travel the furthest. Well, to do that, we need to take the derivative with respect to theta and set it equal to 0. Well, the derivative with respect to theta is equal to what? By chain rule, it's going to be 2 v naught squared cosine of 2 theta divided by g. And we need to find when this equals 0. Well, 2 v naught squared over g is a constant, so really we're just solving for cosine of 2 theta is equal to 0. Between pi and minus pi, this is true when theta is equal to pi over 4. So we see that if we launch our particle at an angle of pi over 4, then it will travel the furthest. You probably learned this in intro physics. So the next problem we're going to look at is a pendulum in polar coordinates. So we're going to have a pendulum attached to a point O right here. It's going to have a length L, and the pendulum is a mass M. We're also going to assume here that the length of the pendulum isn't changing. So L dot is equal to 0. Now this pendulum makes an angle theta with the vertical, so we can identify our basis vectors. R goes out like this, theta hat goes out like this. And next we should look at our forces. Well, there's going to be a force of tension that points inwards like this. My picture is kind of bad, but the tension is going to point minus t in the r hat direction. We're also going to have gravity that points down, force of gravity. So first we should determine what the components of gravity are. Well, if this angle here is theta, then this angle is also theta. So we can use our special angles to determine what the components are. If theta were equal to 0 degrees, and we have that the force of gravity is going to point entirely along the r hat direction. So it's going to be mgr. So here's our pendulum when theta is equal to 0 degrees, and gravity points out in the r hat direction. If theta were equal to 90 degrees, then gravity is going to point entirely along the minus theta hat direction. Here's our pendulum, here's theta hat, and here's the force of gravity, minus theta hat direction. So we have that the force of gravity is going to be equal to mg cosine of theta in the r hat minus mg sine of theta in the theta hat direction. So the next thing we need to do is to write down Newton's laws along both axes. So along the r hat, what do we have? Well, here we have to use mass times our acceleration in polar coordinates. The r component of our acceleration in polar coordinates, which remember from 2 videos ago, is r double dot minus r theta dot squared. And this is equal to our forces in the r direction, which is minus t plus mg cosine of theta. Now, along the theta hat direction, we have m times, and this is our theta component, r theta double dot plus 2m r dot theta dot is going to be equal to minus mg sine of theta. Now we can make this better because we know that r is equal to L, which is also a constant. So the first equation actually becomes minus m L theta dot squared is equal to minus t plus mg cosine of theta. And the second equation is going to become m L theta double dot is equal to minus mg sine of theta. Now technically we could solve both of these equations for theta as a function of time, but the second one is easier. So let's work with that. So we can divide both sides by ml, and we're left with theta double dot is equal to minus g divided by L sine of theta. Written like this equation is not analytically solvable. But what we can do is assume that our pendulum is only oscillating at small angles, so maybe 30 degrees or 40 degrees. And so we can approximate sine of theta to its first order Taylor expansion, which is theta. I highly recommend you brush up on Taylor series expansions if you're not familiar with them. The first term in sine of theta's Taylor series expansion is theta, and so if we assume theta is small, we can make this valid approximation. So this becomes minus g over L theta. I'm not going to solve this differential equation here. We'll work with it in a couple videos when we start talking about oscillations, but this equation is a very important one in physics. It's called the simple harmonic oscillator, and its solutions are sines and cosines. All right, so we're going to work one more example, and this one's kind of fun and also clears up a little misconception that a lot of people have about tension. So suppose we have a particle that's moving in a circle of constant radius. That is a horrible circle. Let me redraw that. So here's our particle of mass m moving at a constant radius. Maybe it makes an angle theta. So first I'm going to draw our basis vectors. We're going to assume that there's one force acting on this particle. It's going to point in the theta hat direction, and we're going to assume that is a constant force in the tangential direction. So we can clearly see that our particle is just going to start speeding up along the circumference. However, I kind of lied. There is another force. It's tension, and of course it points inwards. A common mistake in problems involving a tension is wrongfully assuming that this tension is constant. Here we do not know whether t is constant or is a function of time, so let's just assume it's time dependent and solve for its dependence. So we identified our forces. The next step is to write down our Newton's laws. So along the r hat direction, we have one force. So m r double dot minus r theta dot squared is going to be equal to the r force, which is minus t, and then theta hat direction, we're going to have m r theta double dot. I just realized I stuck an extra m here. I'm sorry. Yeah, the units wouldn't have made sense if I stuck an r an m there. Let's fix that real quick. Apologies. apologies, it's just a 2. So 2 r dot theta dot, and this is going to be equal to f in the theta hat direction. So it's just f. But we know r is constant, and it's also equal to capital R, so these simplify. The first equation becomes minus m capital R theta dot squared is equal to minus t, so the minus signs can cancel. And the second equation becomes m capital R theta double dot is equal to f. So we can't solve this first equation because tension is time dependent, but we can definitely solve the second equation if we know our initial conditions. So let's just assume it starts at an initial angle theta naught and an initial angular velocity omega naught. All right, so solving this equation, we have that theta double dot is equal to f divided by mr. We can integrate once, plug in our initial conditions, and you'll see that theta dot as a function of time is equal to f over mr time plus omega naught. Now we don't need to go any further than this because this equation here only depends on theta dot. So we can just plug it back in. So mr f over mr t plus omega naught squared is equal to tension. So here we have tension as a function of time. And we should see that it's increasing as time goes forward. And this should make sense. It takes an increasing amount of force to keep the mass at a constant radius as the angular velocity increases. Imagine spinning a ball at the end of the rope and keeping it at a constant radius. The faster you spin it, the stronger the tension in the rope in order to keep it at a constant radius. All right, so that about does it for this video on Newton's laws. In the next video, we're actually going to talk about energy conservation. All right, thanks.